Welcome back. Today's topic is inductances in series and parallel. In the last video lecture, we have discussed about self and mutual inductances. We have seen how to determine the inductance of a solenoid, toroid, and also mutual inductances of two windings. So this is the problem which we have, right? So solve this problem. Now, in today's class, we'll discuss about how to determine the effective inductance of two coils when they are connected in series and parallel. Moving ahead, before I move on to this one, I would like to introduce a concept called as coefficient of coupling. Let us suppose there are two coils which are mutually coupled, which means that there is a mutual inductance between them. Coefficient of coupling is defined as K is equal to M by square root of L1, L2. Okay, this is the mutual inductance. M, L1 and L2 are the two coils inductances, and the coefficient of coupling is given by K is equal to M by square root of L1, L2. So now moving ahead now. How to determine the effective inductance when two coils are connected in series. Now see here, there are two coils. This is coil 1 which has a self inductance of L1 and R1, and this is coil number 2 which is having a resistance and inductance of L2, R2, and there is a mutual inductance between these two. So how to determine the equivalent inductance of these two things? Now if you carefully see, this is the voltage drop across this one, this is the voltage drop across this one. You know that V is equal to V1 plus V2, right? So what is V1? V1 is nothing but it is just like a EMF, right? It is minus E1. So what is E1? Now in that one, if I neglect resistance, that EMF, I'll redraw the circuit here. This is L1, L2, and this is M. So what is the EMF in this particular coil? It is L1. The current flowing here is di1 by dt, plus this is the mutual inductance, right? Di. What is the current flowing in this one? It is also again di1 by dt. I'll assume that the same current is flowing in these two coils. So what I'll get? L1 plus M. Similarly for V2 also, what I will be getting? It is L2 di1 by dt plus M di1 by dt. So again I will be getting L2 plus M. So if I join these two, V1 plus V2, since this is equal to V, what I will get? L1 plus M plus L2 plus M di1 by dt, which is nothing but my effective inductance is L1 plus L2 plus 2M. This is my effective inductance. And two coils are connected in series. Now let us suppose if this mutual inductance is opposing them, then what I'll get here L1 minus M. Here I'll get L2 minus M. So here also I'll get L1 plus L2 minus 2M. Okay. So that's why if the mutual coupling is aiding the fluxes, then I'll get it as plus 2M. Otherwise I'll take it as minus 2M. Okay. Now let's see if the coils are connected in parallel. Now this is the case when coils are connected in parallel. Now this is a figure replica of that one when they do have internal resistances. Now I'll consider the easiest one now. Okay. So in this case, the voltage across these two is the same, right? But the currents is varying. So I'll take the net current I is equal to I1 plus I2. Right. So the voltage is same for both of these things. For coil number 1, it is L1 di1 by dt plus M into di2 by dt, because the current flowing in the other coil is different, right? This is I1, this is I2, right? This is So V is equal to, in the first case, it is L1 dI1 by dt plus M di2 by dt. For the second coil, it is L2 di2 by dt plus M di1 by dt. Literally speaking, both are same, right? Because they are connected in parallel. So the voltage also must be the same. So if I equate these two, and if I rearrange them, this is my expression. L1 minus M into di1 by dt is equal to L2 minus M into di2 by dt. Right. So if I again substitute that equation in any of these two terms, this is my expression. Right. Similarly, my other expression also, it remains the same. So if I add these two equations, what I'll get, and you solve them, you'll get this final expression. The effective inductance is L1 L2 minus M square by L1 L plus L2 minus 2M. This is the final expression for effective inductance when inductances are connected in parallel. That too when the mutual coupling is aiding them. If it is opposing them, you will get here plus. Okay, so now I will write the four cases. If they are series aiding, it is L1 plus L2 plus 2M. If it is series opposing, it is L1 plus L2 minus 2M. If it is parallel aiding, it is L1 L2 minus M square by L1 plus L2 minus 2M. If it is parallel opposing, these are the cases. Okay, so practice these problems at home. We'll solve them in the class. Okay, thank you.